Okay, so here's a continuation. We're in class 3, and this is video 2. And what we're going to deal with today in this section is compressible and incompressible. I guess we'll start with incompressible density. We're mostly going to be interested in the incompressible for the pressure gradient right here. So incompressible, what we want to remember, we want to associate the density is assumed to be constant, right? So we have constant density, and the general equation that we had in the last class, right, that we developed, or not the last class, but the last video, we had this right here where we said the gradient of the pressure minus the specific weight, and that was only affected in the z direction, is going to be equal to rho times A, and this is really F equals MA right here, being treated, and this on a per volume basis. That's why we don't see that's why we have density right here. But if it's statics, fluid statics, we could reduce that to 0 for statics. And just specifically in the z direction, we had the differential of pressure with respect to z was going to be equal to negative specific weight. So in practicality, what this becomes when we're going to go to apply it is simply going to be, if we have two different pressures across two different places, P1 and P2, and maybe measure it between z, and call the difference between z maybe the height. A lot of times we'll use height, but actually that that h might want to refer to that as head. That is generally the thing, so we use head, and sometimes we think of pressure as in terms of the head that's on the thing. And so we would write as a general equation, P1 is equal to gamma h, the head, plus P2, right? So this is really the general practical equation that we're going to use for many things. And if we want to define head, we would just say it's the difference in pressure between two places divided by the specific weight. And head is measured in, well, often in feet, but it could be meters and other things. So when we go to apply this, we might have multiple ones of this right here for different separate things, and separate like levels or layers, if we have different layers of different types of fluids. But for the time being, we'll just think of it as, if we want to find the pressure at a given point somewhere, we take the pressure at the top, which is often going to be atmosphere, and we'll often treat that as if it's 0 right here. And see if we can get the camera to focus here. There you go, give some of the focus on. So when you're thinking of that kind of, what is the pressure that's being experienced down here at the bottom, you could think of it as almost a column of water, right? But it doesn't have to be a column. Like, you could have some kind of weird vase. Like if I had a weird vase that looked like this right here, and here is where the level of the top of the vase is, and it's open to the atmosphere. If I had a pressure point right there, right, the pressure that was at that point, because of all the water above it, it wouldn't be any different than if I had a column of stuff in the same thing. If this height were the same right here, if this head level, we would get the same pressure right in there. So bear that in mind when we're looking to try to establish what the pressure head is on something. Quite often, one of the things that we'll use besides water, we'll use mercury as actually a means of measuring the pressure in something. So we're not only going to find what forces are caused by this distribution, this pressure gradient in the vertical axis, we're also going to use this effect to be able to measure pressure, especially for very slight changes in pressure. And that's what we're going to deal with manometers probably in the next video, because I'm going so slow here. Okay, so when we might as well also refer to gases. We just did liquids when it comes to the same type of treatment, and of course gases are pretty much assumed to have a variable density, so they're compressible right here. So that means that density varies. If you when you hear compressible, think about the density varying. And here's the equation that we just wrote up above, right? That the pressure, differential pressure, as you go in the vertical axis is equal to negative, because it's increasing as you go downwards, gamma. And that's, of course, that's density times gravity, that gamma. So we could do this in terms of the ideal gas law. Noteworthy that the differential pressure right here can be related to, we could stick this over to the other side, right? We could say that this is equal to this right here. Pull them over to the other side, so it's negative pressure times gravity divided by gas constant divided by temperature. And if we were to integrate this, you'd know that you'd get the natural log, right? Because integrating, so when we would flip this thing around, we'd have to take this pressure and bring him onto the other side to be able to do that integration. Therefore, we get a natural log. And so here's the pressure at a particular point, and here's like a reference pressure that you would put in here. So if you want to find the pressure where P1 is a known pressure, normally we would take the inverse of the natural log, which is going to be the E, and we'd raise it to the, it's going to be hard to squeeze all this in here, but it's the concept that matters more than the execution here. It'd be negative G over RT. I need to make that box bigger, darn. And then we'd have like Z minus Z1. All right, so that doesn't really fit there. We're not really going to use this equation for anything, but we should think of it in terms of here's a comparison between what's going on with the liquids. Here's what's happening with the gases. And when does this matter? It's really about like high altitudes, right? So this is, sort of a, because it's the ideal gas law that this is based on. So this isn't 100% true, but you could tell that the high altitudes versus sea level, that variation can be related based on this theory, right? Not theory, but based on this mindset, this equation right here that we derived, or we came up with an explanation for, at least in the previous video. So high altitude versus sea level, that's when this is going to matter to us for gases, and note that it's an exponential relationship. I think I can fit in an example in here. So I'm going to continue with this page onto this video. Let's see. Let me put it back on here. All right, so in here, so we're trying to use some of this idea before we get into manometers and pressure measurement. So there's this leak in a buried gasoline storage tank, and water seeped into the tank, and it settles to the bottom because gasoline has a specific gravity. At least this gasoline has a specific gravity of 0.68. We want to determine the pressure at the water, so like a gasoline interface, like right there, and at the bottom of the tank. When do we have to do it at the bottom of the tank too? No, I think we just had it. Yeah, we want to do it at the bottom of the tank too. Might as well. So what we want to do is we're going to start at the top and work our way down. Right. So I'm going to call this pressure right here. I often will call atmospheric pressure P0. I'm going to call this 0.1, and I'm going to call this 0.2. So this could be P1 here and P2 right there. What is the pressure at the top of the surface of the gasoline, right? So we're going to assume that it's going to be, am I going to do that? No, I'm going to go ahead and use atmosphere as being 0. So we're going to treat it like gauge pressure, all the pressures we're going to answer with this. And so it's the most common, and so we're going to use it unless we're going to say that it's going to be absolute. So if we want to find the pressure at 1, we swim downwards from the top and get down there. So we say that P1 is equal to the gamma of gasoline, and I'm just going to write gas, times H1, and I'm going to call this H1 right here. So H1 is equal to 17 feet plus P0, which is atmospheric right there, right? So because we could look up this gasoline, but we're actually given the specific gravity. So all we need to do is multiply the specific gravity times the weight density, or the specific weight of water, which we're going to use pounds force right here, or just regular pounds. So 62.4 pounds per cubic foot. And all you have to do is, make sure you use the same units. We'll use feet here. So that's going to be 17 feet plus 0 for the atmospheric pressure. And what we end up with is 72.1. What did I get that? No, 721. Sorry, I misread my own notes here. 721.3 pounds per cubic foot. And no, square foot. Need to fix that on my notes. I wrote cubic feet for some reason. It's square feet, right? So this is pounds per cubic foot times feet, so you get pounds per square foot. And then might as well give this in PSI, right? It's what we're more used to, PSI. So we have 721.3, and we'll divide it by 144, right? So that's inches squared per foot squared, and that's going to give us 5.009 PSI. And because it's gauge pressure, let's make sure we're clear that it's gauge pressure. If we just wrote PSI, we'd probably assume that it's gauge pressure. We also might want to know the head here, right? So if the head is of this, right, it's not going to be 17 feet because this is really good. That would be what we would consider for water, but we're going to use water as the reference right here. So what we'll do is we'll take our 721 and divide it by the weight density of water, and that's going to give us how many equivalent feet of water would give you the same pressure, right? It's this idea of head being something that's like a useful way of thinking of pressure, right? Thinking of how much water would be equivalent to it. And now if we want to get the pressure at 2, we could just say pressure at 2 is equal to, now it's going to be water that's in here. So I'll write the H2O times H2, which I'm going to call that H2 up above, plus P1, right? So we're swimming downwards still. And we're going to continue to do that in the manometers coming up soon. So here, all we're going to have is 62.4 in the head, which is 3, right? For this, or the height change, you could call it, think of it in those terms. And then 721.3. And now we're with 908.5 pounds per square foot. But of course, we'd rather have this in PSIG. So it's 908.5 divided by our 62.4. And that's going to give us 6.309 PSIG. And then if we wanted the head, I could call it H, but it's going to be easier because we already called this H up here. I'm going to call this as a specific thing we're going to call head. And that's 908.5 divided by 62.4. Whoop, I made a mistake up here. I'm sorry. I looked down at the wrong line right here. This is supposed to be 144. Darn. Oh well, we'll keep it. So we had 14.56 feet of H2O. Well, actually, we could have just added 3 to this right here because this part of it was water, right? Well, whatever. All right, so here's like some out of another book right here that wanted to compare the column heights of water and carbon tetrachloride and mercury, right? Corresponding to a pressure of 50 kPa or kilopascals. So we're going to use metric here. That's one of the reasons why I included it here, because we were doing everything in British gravitational up above. So all we have to do really is find the height, right? So we're at the height of water for 50 kilopascals, and 50 kilopascals, we can take kilopascals, and if we have the weight density of water in kilonewtons per meter squared, which is 9.81 kilonewton per meter cubed. Yeah, the cubed. That's supposed to be cubed right there. I have it written wrong on my page. There you go. And you can look this up in our table that we use for the equation sheet, for exam equation sheet. We will end up getting 5.10 meters. I just kept it to 3 sig figs right here for the thing. Compare that to carbon tetrachloride, which is CCl4, and 50. We don't have to use units. We already established that. This is kilonewtons per meter squared, so kilonewtons per meter cubed is going to give us that that height. And so we can look this up and see that's 15.6 kilonewtons per meter cubed, or 3.21 meters is what we end up with. And then we can see what is required with mercury, and that's a pretty stark difference because it's got like a specific gravity over 13. So it says 133 kilonewtons per cubic meter is what we have for our mercury here, and we end up with 0.376 meters. So this is a huge difference. Of course, we would expect it, right? Because it's like 13 times as dense. You would think it'd be 13 times as much of a height that you would need to establish that. And then lastly here, let's see what this is just a demonstration of gauge versus absolute pressure. So on the inlet side of a pump, a board-on pressure gauge, which we're about to see what this is. So we should actually I actually wrote skip this and then come back to it. So maybe that's what I'm going to do. I'm going to skip this and come back to it. So I'm done with this video, and we're right there near the 15-minute mark, actually 16-minute mark. That's okay.